Hello everyone, welcome to another particular lecture. So this is our second lecture or the final lecture of our discussion regarding protection and deprotection strategies. So in our previous lecture we are discussing about the what is the protection and deprotection and their importance, as well as we are discussing about the amine group protection and deprotection strategies in elaborate way. So in this particular class, we are actually looking for the different functional group protections such as alcohol group protection, carbonyl group protection, and acid group protections, and their deprotection strategies. So we are begin with our class with the alcohol group protection. So the main and the important way to protect the primary alcohols are the silyl mediated protection. So what happened that basically we are using a silyl group and react with the alcohol to make the silyl ether complex, and the silyl ether are actually nothing but protecting the alcohol group. So there are different common silyl protecting groups are there, such as the TMS, trimethyl silyl. So this compound, the TMSCl, also TBDMS, tetrabutyl dimethyl silate, silyl, this one, and TIPS, triisopropyl phenyl silyl. So this type of silyls are actually used to protect the primary alcohol. Okay, so the reagents are silyl chloride and a base. Basically, imidazole or pyridine are used for this particular silyl mediated protection. And the deprotection method is whenever the silyl ether has been formed, any kind of fluorine source will actually clip the silyl oxygen bond, and ultimately deprotection has happened. And due to this, there is a fluoride ion or acidic condition has been used. The reagent is tetrabutyl ammonium fluoride (TBAF) or acid like HCl, and the deprotection reaction is something like this. This is the silyl ether. This is a protected form of our primary alcohol. React with the tetrabutyl ammonium fluoride to getting our corresponding alcohol back, as well as the byproducts. Okay. Now we are moved to our second type of alcohol protection, that is the trityl protection, that is TR. And the reagent is triphenyl carbon chloride. So this is our particular reagent for this particular trityl protection. And the interesting thing is it can selectively protect the primary alcohol over secondary alcohol, because of the thing is the this particular TR group is a bulky enough. That's why actually it prefers to actually prefers to protect the primary alcohol in presence of secondary alcohol. So this is the reaction, and how the deprotection has been done. The deprotection has been done by the hydrolysis or a nucleophilic substitution reactions. Also, alcohol group can be protected by forming their corresponding ethers. Okay, so there is a common ether protecting groups is there, such as methyl ether, or there is the MOM, that is methoxymethyl benzyl ether, as well as the benzyl chloride was there, and THP also there, tetrahydropyranil was there, where the dihydropyran has been used to protect the alcohol group by forming alcohol to ether. Okay, so first of all, let us talk about the MOM ether. So the reagent is MOMCl and a base, especially DIPA has been used to protect this particular compound. And then the reaction is something like this. Here it is our secondary alcohol, and secondary alcohol react with this particular MOMCl, as well as in DIPA as a base to form this type of protection. And the deprotection strategy is by using acidic hydrolysis, where dilute HCl or other acid has been used in aqueous medium to regenerate our corresponding alcohol. Now the BN ethers. We already discussed very much about the BN during our amine protection, and in that particular part actually we are discussing that how a BN actually used for the amine group protection as well as the alcohol group protection. So here the benzyl chloride and a base can be used to protect the alcohol. There is a secondary alcohol here, and it will be protected from something like this. And after that, the hydrogenolysis, or by treating with hydrogen palladium charcoal to regenerate our corresponding alcohol. Okay, and also the THP ether. THP is a dihydropyran and acid catalyst used. The acid catalyst is mainly a source of hydrogen. So paratoluenic sulfonic acid also used in that particular part. And the deprotection method is the acidic hydrolysis. That's similar to the MOA method formation. And the reagent is dilute HCl or other acids. Okay. So let us talk about the diol protection. Like for the case of alcohol, there is a single OH is there. But what happens if there are diol present? So diol can be protected by incorporating carbonyls in presence of acid catalysis. Like here, this is the 1,2 diol and this is the 1,3 diol. So here basically uh, carbonyl group is there, acetone is adding with presence of acid to mask this particular diol by forming this type of 5-member ring. But here in the catch is that in the case of 1,2 diol, only cis diol can be protected by this formula, trans diol can't be protected by this method. But in the case of 1,3 diols, there is a no issue in the case of cis trans, like both of the cis and trans diol can be protected by this type of method. And the deprotection is a very simple, like similarly acidic hydrolysis was there because this particular process is a reversible in nature. And that's why actually the deprotection can be done by using simply acidic hydrolysis or adding like dilute acid like aqueous HCl or aqueous H2SO4 will do the deprotection part. Now also there is a other methods are there to protect the diols. First in the using the acetals, hemiacetals, hemiketal can be used to protect this particular group by using by preparing this type of 5-member rings, and the deprotection strategy is similar to the acidic hydrolysis. Similarly, a carbonate protecting group was also there, like trifosine used to protect the diols in presence of pyridine, and also silyls are also used to protect this type of uh, diols by making this type of 5-member silyl oxygen type of 5-member ring formation. Okay, so now let us move over the carbonyl group protection. The important carbonyl group protections are by protecting acetals and ketal formations, and the second way to for protect the carbonyl group is to by preparing thioacetal and thioketal formation, and the third one is the oxime and hydrazone formation. So this is the acetyl protection, this is the thioacetal protection where thiols are used to generate the acetals, and as well as the oxime and hydrazones protections. So let us bring our discussion with the acetal protection. So acetal protection, the protecting reagents are the diols and alcohol. So if you think closely, then it is completely opposite of diol protection, where in the case of diol, we are using a carbonyl compound such as acetone and all to protect the diol. Here we are using diol to protect the carbonyl. So these two are actually we can say that similar kind of strategies, but a little bit of difference, like kind of mirror image type of thing. We can give analogy like that. So what happened that here the carbonyl group are actually treated with the acid and some kind of methanol to form this type of acetals, and also in presence of diols uh, in acidic hydrolysis it can produce this type of 5-member ring to protect the particular carbonyl group. And the deprotection method is also the acidic hydrolysis, like the reaction are reversible in nature and the reagents are dilute acids such as the aqueous HCl or aqueous H2SO4. So let us understand the mechanism of the particular reaction. Like here, first of all, that particular H plus are used. So this H plus actually coordinate with the carbonyl oxygen. So and after that particular coordinate, the carbon become much more electrophilic in nature, and that's why this OH will attack to form this type of compound. And then again a rapid proton transfer has been observed. This particular proton has goes to here, and again it will lead to the sudden increase in a electrophilicity in this particular carbonyl carbon, and that's why this OH will attack, and this particular H2O goes out of the medium, and then after the deprotonation we got the protected form. Similar strategy has been applied for the deprotection as well, where the acidic hydrogen H plus will get coordinated with this, and then H2O will attack here, and the similar reversible strategy has been done for the deprotection strategy. And basically the protection and deprotection is highly dependent upon the concentration of the acid present in the medium, since it is a reversible in nature. Okay, so now let us talk about thioacetal or thioketal mediated protection strategies. So here thiols and an acid catalysis has been used to protect the particular carbonyl compound by preparing a thioacetal or thioketal formation. So basically, this is a thiol can react with a particular carbonyl compound, and here in presence of acid catalysis, we can use uh, Lewis acid also, just because since the thiol having the lesser electron donating capability or the lesser nucleophilicity, so this particular carbonyl electrophilicity of this particular carbonyl carbon has been increased so much so that this particular attack can be feasible, and that's why the Lewis acid has been used. And after protection, the deprotection strategy is very unique here. Like for deprotection, either you are use Raney nickel desulfonization or oxidative hydrolysis. For desulfonization, Raney nickel and hydrogen can be used, and for oxidative hydrolysis, mercurous chloride or HGS can be used to deprotect the particular thioketals. Now let us talk about the oxime and hydrogens. Oxime and hydrogen can be generated from the carbonyl group itself by treating with hydroxylamine or hydrazines. So they will react to form the oxime and hydrogens, and the deprotection method is a simple hydrolysis while using the dilute HCl or acid or base reaction will easily deprotect this particular oxime and hydrogens. Okay, so now let us talk about the protection of acid groups. So general way to protect acid group is to generate an ester, because acid to ester generation is very easy. So ester protection general strategy is to can be hydrolyzed under acidic condition or basic conditions. So there is a different ester has been produced, such as the benzyl ester, methyl ester, and tert butyl ester can be prepared and easily and this particular ester uh, protection can be easily removed by adding strong acid or hydrolysis pathway. So here this is the acid group. Acid group react with the excess alcohol in presence of strong acid to form this type of ester, and also the CH2N2 or DCC coupling was also used to generate the corresponding ester from the acid group. And the deprotection strategy is to strong acid treatment or hydrolysis. Now let us talk about the double bond and triple bond protection. So if your compound contains a double bond, the double bond can be protected by two different pathways. Either it will form a three-member ring, or it can be form a epoxide. So for three-member ring, basically three-member ring can be generated by using the Simmons-Smith reaction, where the CH2I2 in presence of zinc copper can generate this type of protected form of the double bond by forming a cyclopropane ring. And the deprotection of this particular ring is by treating with aqueous acid. Then the cyclopropane ring breaks apart and it will again regenerate our double bond. Also, we can do the epoxidation pathway. So epoxidation, MCPPA used for the epoxidation, and by epoxidation we are actually protecting this particular uh, double bond. And to uh, and to deprotect, we are simply adding dilute acid or base to get our desired compound back. And for the triple bond protection, basically there is a metal complex formation has been observed, has been used for the triple bond protection, dicobalt hexacarbonyl complexes. The reagent is dicobalt octacarbonyl, CO2CO8. So what happened that this type of triple bond is there, and this triple bond is treated with this particular group, this particular metal complex CO8 to generate this type of a metal complex form, and thus the triple bond is protected. And to deprotection strategy, oxidative cleavage has been observed, and in oxidative cleavage either it can be done by using the BH3 or NaOH H2O2, or iodine or sodium ammonium nitrate also do the deprotection of this particular metal complex bond. So with this we have to end this particular chapter, and in this particular lecture we are understand that what is the method of the alcohol group protection, primary alcohol, secondary alcohol protection. We are talking about the diol protections, as well as we are talking about the carbonyl group protection, the three different protections like acetyl formation, thioketal formations, and the hydroxyme and oxime formations. After that, we are talking about the acid group protection by uh, treating acid to ester conversion through protection, and after that, we are talking about the double bond and triple bond protection. So I think that it will be enough for this particular chapter. So from the next video onwards, we are looking for some kind of next chapters. So thank you for listening. So we have end this particular chapter here.